Good afternoon and welcome to all of you to the problem solving session 6 of the course Advanced Soil Mechanics taught by Professor Sridhar Shekaran, Department of Civil Engineering, Indian Institute of Technology Guwahati, and I am your teaching assistant for this course, Mujibur Rahman from the Department of Civil Engineering, IIT Madras. So in this course also we will be dealing with the shear strength of cohesionless and cohesive soils, and as you know that in the last session we uh, learned about the pore water pressure parameters, Skimton's parameters, Hankel's parameters, the relation between them. Now in this week 6 we will be going through the triaxial testing and the different tests that we are doing in the conventional triaxial setup, and how we are interpreting the results, or how we are interpreting the different tests that we are doing in the triaxial test or conventional triaxial setup. So this is a conventional triaxial setup, and this triaxial testing, if we talk about the triaxial testing, why we want if we are having a direct shear test, what was the need of going to the triaxial test? So the first thing is that in the direct shear test we have a limit of the type of material that we can use in the direct shear test. In the direct shear test also we are not able to control the drainage. Pore water pressure parameters or pore pressure measurements cannot be done there, and we are sharing the sample over a predetermined horizontal surface, correct? But in this, all the limitations of the direct shear test that have been overcome in the triaxial test, where like the shear strength parameters or whatever the shear strength tests we are doing for soils, we have control over the drainage, we have the control over the drainage conditions, and also whatever the pore water pressure we generated during the test, we can measure that. And it's not a material specific, we can do the testings on a wide range of materials, unlike in the direct shear test. So it is a typical setup of the triaxial test. It involves it has a base pedestal over which you can see there are three inlets, cell pressure, three inlets for the cell pressure. There are three inlets, one for the cell pressure, one for the pore pressure measurement, and another is for drainage or back pressure. Then we have a bottom cap, and this back pressure and pore water pressure measurements are actually connected to the sample, correct? You see, they are going into the sample here and from here, and this cell pressure is actually it is connected to the surrounding of this sample outside this, correct? And we have this is a confining chamber, correct? And in this confining chamber we usually put our specimen, and the specimen, it's not like we prepare the specimen and directly pour it, mount it on the pedestal. We have a proper arrangement for it. So we have the bottom cap, porous disc, and then we fill this material inside a membrane so as it should not come in contact with the water present in the confining chamber. Then again on the top we have the porous disc top cap, and this bottom cap and top cap are actually for applying the loadings. This porous disc, it allows the dissipation of the water, and over this porous we used to have a we call it there is a sheet of paper that we used to cover this porous disc so that the particles of the soil should not get trapped in the porous disc. I forgot the name, but yes, there used to be a kind of a paper which is used for covering this porous disc. Then between this porous disc we have the soil sample, right? And this axial load is applied through a plunger by means of this ball valve, and this is this circular thing that you are seeing here. It ensures that there is only axial load that is being applied on the soil sample. In case there is a misalignment of the sample and the plunger, there may be some kind of movement. So this ball ensures that there will be only a vertical load, axial load acting on the soil sample, correct? And there is a higher bleed value, fine. So this is a typical conventional triaxial setup, correct? Now what are the different tests that we are performing in this triaxial setup? So the different tests that we are doing in the triaxial setup is the first unconsolidated undrained test, consolidated undrained test, and consolidated drained test. Now, what is this unconsolidated undrained test? Generally, in the triaxial, as we go in the lecture, in the further slides, there are we will see there are different stages of the triaxial testing. It's not a single stage test; it's a multi-stage test. It has a three sub stage. One is the saturation stage, then we have a consolidation stage, and then the shearing stage. So, and at this moment, just remember it's a three-stage process. It has a saturation stage, it has a consolidation stage, and it has a shearing stage. Now, what is this unconsolidated undrained test? It's a type of the test that we perform in the triaxial where we are not allowing any kind of drainage to happen during the consolidation phase, nor nor during the shearing phase. So it means that there is initial consolidation. So what is the consolidation? Consolidation is the change in volume due to the expulsion of pore water. Correct. So when there is no consolidation, so there will be there is no, since we are not allowing the water to come out from the sample during consolidation stage, so it means that there is no initial consolidation that is going to happen for this unconsolidated undrained test. Correct. And during loading also, there we are not allowing this water to escape out. So in both the stages, whether it is consolidation stage or the shearing stage, we are not allowing the drainage. That's why this test is a quick test. Now another test is consolidated undrained test. As the name suggests, you can think of this is a stage 2 name and this is a stage 3 name. I can simply just highlight it here. This corresponds to, if I write consolidated drained, for example, so this corresponds to stage 2 and this corresponds to stage 3. Correct. And stage 2 can have either consolidated or it can be unconsolidated. Or unconfined. Because in the there is a one more test that's a part of the unconsolidated undrained test. So stage 3 can be either drained or undrained. So the naming of this test is as per the states. So unconsolidated undrained, it means that there is no drainage of water during consolidation and there is no drainage of water during the shearing process. Now consolidated undrained test, it means that water is allowed during the consolidation process, or we are allowing the sample to consolidate under a cell pressure. And undrained means during the undrained stage we are turning off the drainage values so as there is a generation of the pore water pressure. Now the last test or the third test is consolidated drainage. Consolidated drainage is we are allowing the sample to consolidate under the cell pressure, and during the shearing stage also, due to the application of the load, we are allowing the water to escape out from the soil. And the in terms of the time that they take for completion, or for the time taken for the completion of the test, this UU test is a quick test, consolidated undrained test is relatively slow, and consolidated drainage is very slow, because we want, if the rate of loading, because we have seen in the last week that the rate of loading affects the generation of pore water pressure. If the rate of loading is high, so even if it is a permeable soil, in the rate of loading is high, it means that there will be there may be the cases that the pore water pressure will generate. So that's why we have to take care of the rate of the loading also, and that is the reason that this test is slow. Now, if we talk about the first test, unconsolidated undrained test. So as I told you, there is no drainage and consolidation during confining and loading. There is no drainage and no consolidation during confining and loading stage. Both the things are restricted. Consolidation is restricted, and during shearing there is no drainage. Fine. So when there is no consolidation, we are not allowing the drainage to happen also. So generally this test there is no use of the pore water pressure. Why? You will come to know when we draw the Mohr circle for this test. And it's generally we call it, we are preferring the total stress analysis. This, what are the analysis we are doing in this test is a total stress analysis. Confining stress is applied and specimen is shear, fine, and the rate of loading is fast, and the result is, and it results in the quick failure. This unconsolidated undrained test, generally the rate of loading is fast, so that there is the condition prevail will be the undrained. Now if you see the stress conditions, in the stage 1 we have the saturation. Saturation ensures that B value is greater than 1. Sorry, B value is greater than 0.95, correct? Because it's not like we will not be able to achieve the B value of 1. So generally we are assuming that if B value is greater than 0.95 during saturation, then our sample is saturated. Then once we enter in the consolidation phase, we are not allowing the pore water pressure to dissipate. Not a pore water pressure, but we are not allowing the water to escape out during the consolidation. So as a result of which there will be the generation of some pore water pressure during the confinement stage. And during the shearing stage also, when we apply the divatric stress, there is the generation of pore water pressure in addition to this confining, the pore water pressure that gets generated during the confining stage. So this is stress conditions or the stress conditions for the unconsolidated undrained test. Now the second test is consolidated undrained test. Fine. So what do you mean by consolidated undrained test? The drainage is allowed during the confining stage, and which results in the isotropic consolidation. What isotropic consolidation means that the consolidation will be carried out under a confining stress which will be equal in all directions. You can see sigma 3, sigma 3, sigma 3, sigma 3 L. And you have seen in this in the module 2 or module 3, the when we have a uniform stresses around a sample of soil, it will result in the volume change. So the drainage is allowed during the confining stage. It results in the isotropic consolidation. What do you mean isotropic consolidation? Means there will be some volume change in the sample. And after consolidation stage, once the consolidation stage is over, either the pore water pressure will be 0 or it will be equivalent to the back pressure. So in the how it will be equivalent to 0 or back pressure, I will tell you in the subsequent slides. And axial load is measured and pore water pressure is measured till failure. Both when we are sharing the sample, then axial load is measured and the pore water pressure is also measured during the test. Loading should be at slower rate to ensure proper development of pore water pressure. Now, as I told you that what is happening that when we are loading the sample in the triaxial, generally if you see here, if I will, yeah, you can see here, pore water pressure measurements are done here at the base and back pressure is applied at the top, correct? So when this back pressure, when the consolidation pressure, since at this moment we have not introduced you to the term cell pressure and back pressure, but for you might have seen the lectures and you might have aware with these terms now. So when we are applying the back pressure or the pressure from the top, it needs some time to get equilibrated in the sample, and then only it will reflect some measurement at this point at the pore water pressure transducer here, which is connected at this point. So there it needs some time for the pore water pressure to get equilibrated, and that's why we need this test has to be it has to perform at a slower rate. And this you can see that the stress conditions, stage 1 is the saturation stage where B value is greater than 0.95. Then we have the confining stage, isotropic consolidation, and it's a drainage where the water is allowed to escape, and the shearing part. In the shearing, it's undrained, so it means that due to the application of sigma D and the drainage value is closer, there is a generation of the pore water pressure, that is UF. Now another test is consolidated drainage test. In the consolidated drainage test, drainage is allowed at both stages of the loading, at both stages, whether it is consolidation or whether it is shearing stage. And volume of water expelled with time during consolidated stage is important. Why? Because whatever the volume of water will come out during the consolidation phase, that will determine the what will be the rate of shearing in the shearing stage. All the results are in terms of effective stress. Pore water pressure is not expected throughout the test because we are not allowing the pore water pressure to get generated in the sample. So the rate of loading has to be slow so that there is no development of the pore water pressure. So this is just a brief overview of the three different tests that we perform in the conventional triaxial. Now, as I told you, there are the different stages of the triaxial test. Please note that these stages of triaxial, these are meant for the consolidation drained and consolidated undrained. For the unconsolidated undrained test, we are actually simply applying the, we are not like, we are ensuring for this test, unconsolidated undrained test, we are bringing the sample, ensuring that it is saturated, then applying this pressure, cell pressure, applying the consolidation pressure, whatever be the desired, and then we are shearing it. There is no concept of this consolidation stage, or there is no concept of the shearing, this undrained shearing, or I mean say there is no concept of the this drained and undrained shearing. We are doing the undrained shearing, this drainage value will be closed and we will directly shear the sample, correct? So these stages are mainly stages of triaxial are mainly for the CDCU. The first thing is the saturation stage. Now, what is this stage? What was the need of doing this saturation? Whatever the triaxial test we have to perform on any, whatever the type of soil we will use for doing the triaxial test, we have to ensure that the soil is saturated. So for doing this, for achieving the saturation, we are using a back pressure. What the back pressure is? It's actually the water pressure applied to the soil pore water to force the air present in the voids, if any, to dissolve in the water. So then the main purpose of this back pressure is to ensure that there is no air in the soil. If any portion or if any volume of the soil, if any air is present in the soil, we are applying the water pressure so that this air is getting dissolved in the water. It ensures that in every part of the soil, in every void of the soil, there should be water. So the back pressure is like increasing the pore water pressure without altering the initial effective stress conditions of the soil. This is very important. So whatever the back pressure we should be applying, we should apply to the soil sample. We have to ensure that it should not alter the initial effective stress conditions of the soil. And generally this B value is obtained using the Skimton's equation. B is called delta U by delta sigma 3. Now here I want to spend some time, like, yeah. So now here B is called delta U by delta sigma 3. Yes. Like we have when we take the triaxial sample, we are applying the cell pressure from outside. It's a outside means it's a soil sample, correct? And we have a confining cell. Fine. So this cell pressure gets applied outside the soil sample, correct? So this is cell pressure. This back pressure is applied and it gets directly into the sample. This back pressure is applied directly to the soil sample. As I told you, it's the back pressure is actually the water pressure which is applied to ensure the full saturation of the water. Now this cell pressure should be always greater than back pressure. Why? The reason is, at any moment of time, if our back pressure, so if we are applying the back pressure, it means that we are applying some load like this, some pressure like this. So at any moment of time, if our back pressure is greater than cell pressure, what is happening? The soil will start to bulge out. So our sample will get disturbed. So we have to again repeat the process. We have to again prepare the sample, do the saturation again. So now, how we are calculating this B as delta U by delta sigma 3? Initially, when we start mounting the sample, once we complete mounting the sample, we will apply a small amount of cell pressure. Once we mount the soil, if it is clay, we don't need like a initial cell pressure, because this clay will be able to hold without any confinement, because it has a cohesion in it. But if we talk about the sands, we need a little amount of vacuum initially when we mount it on the pedestal, Then once we fill the pedestal, this confining cell with water, we have to apply a confining this cell pressure, so as this water should be able to hold the specimen. Fine. Now once, let's assume we have kept the initial cell pressure of, let's assume 20 kPa. Fine. 20 kPa was the initial cell pressure for holding the specimen of soil. Now after this stage, whatever I will be discussing, this is true for both clays as well as sand. Now at this moment, since either the sample can have some amount of water in it if it is a clay, and if it is dry sand, there will be no chance of having a water in it, or it is not saturated. So we are actually doing one thing. We will apply the back pressure and increase it to 10 kPa, let's assume. And we have to ensure that the difference is always, like the cell pressure is always greater than back pressure. Now when this 10 kPa is applied on the sample, so some water will go into the sample. Let's assume this is the volume of water which is going into the sample. Now after some time, what will happen, that this volume of water that is going into the sample will be constant. At this point of time, this whole back pressure will get equilibrated in the sample. And since pore water pressure transducer is also attached to the same soil and at the top, this pore water pressure transducer will measure the pore water pressure value, which will be close to this 10 kPa. Correct? At this time, we will say, okay, at this 10, when we have applied the back pressure of 10 kPa, this has got equilibrated in the sample. Now we want to check whether at this value of back pressure, did the sample is saturated. So what we will do, we will close the back pressure value. We will close the back pressure value, and at this point, the U pore water pressure is U initial is 10 kPa. Correct? Now what I will do, I will increase the cell pressure to, let's assume 50 kPa. So what is the change in this sigma cell pressure? So cell pressure changes 50 minus 20 is 30 kPa. Now due to this 30 kPa, there will be the generation of excess pore water pressure, and this excess pore water pressure, we call it U final. Let's assume it is 20 kPa. So what is the change in U? 20 minus 10 is 10. So if we calculate B is 10 divided by 30, is 1 by 3. So it means that this B value is less than 0.95. So we have to again start this loop, start this stage. We will again, what we'll do now, we will hold the cell pressure at 50 kPa and increase back pressure to next interval. Let's assume I want to give an interval of 20 kPa. So initially it was 20, 10, then I want to give plus 20, it is 30 kPa. Correct? So now this 30 kPa will get applied to the soil sample, and again there will be some water will go into the soil, and it will get constant after some time, and after this 30 kPa will get equilibrated, and this pore water pressure transducer will measure a 30 kPa. Fine. So we have to loop this way, this procedure, and once we will achieve this p value of 0.95, we will stop. We will say, okay, our sample is saturated. Fine. So this is the way we do in the labs. Fine. So also, as I told you, it has written that back pressure is like raising the U without altering the initial effective stress conditions of the soil. So B is calculated delta U by delta sigma 3 as I show here, and cell pressure should be always greater than back pressure. In case if it is greater than back pressure, then it will start bulging. So let's assume that U initial effective stress conditions sigma 3 I dash is sigma 3 minus U, and once we apply the back pressure, there is some generation of the pore water pressure, and as per the Skip-Turns equation, delta U is equal to delta sigma 3 for a saturated soil. This is saturated. This is the like once the soil is saturated. So delta U, whatever be the change in the applied sigma 3, it should reflect in the delta U. So that's why delta sigma 3 is written as delta sigma U. So once you do this, like you determine the effective stress, final effective stress condition, it comes equal to the initial stress conditions. Correct? So main thing is, once it is saturated, once the soil becomes saturated, this equation holds true. Delta sigma 3 is equal to delta sigma U, as a result of which our final effective stress conditions become equal to the initial effective stress conditions. Right? Now what is the use of back pressure? So it's used for saturation, and once the back pressure is applied to the saturation will not happen instantly. Why? Because this water pressure will take some time to dissolve this air, and for equilibrating throughout the sample, it takes some time. Each increment should be small enough, and equilibrium time should be long. Yeah. For example, if we assume that our sample will get saturated at a back pressure of 200 kPa, so we don't have to apply this 200 kPa at a single instant. Or if there are two ways of doing it, either we can do the saturation in the incremental method. So we can do this back pressure either by incremental method, or we will give this back pressure directly and keep the sample for the saturation for 1 or 2 days. And after 1 or 2 days, we will check what's the B parameter. And once this B parameter is greater than 0.95, we will start the shearing stage, consolidation stage. And this equilibrium time permits air displacement and water saturation. And change in back pressure after the back pressure application needs to be monitored till it reaches the equilibrium. As I told, two ways are to do it. Either we want to monitor the back pressure, or we can monitor the pore water pressure line, because same thing will get reflected in the pore pressure transducer. B parameter need to be checked at the end of equilibration time. Fine, as I told you, one is our sample reach in the sample where the back pressure reach like there is no further fluctuations in the back pressure, we have to check the this B value. If B value obtained is less than 0.95, the process of back pressure increment is repeated. As I told you, there are two ways of doing this saturation. Either we can do an incremental method, or we can do a like we know that sample will get saturated at 200 kPa, 300 kPa, we will give it directly 200, 300 kPa and keep it for 1 or 2 days. And in the incremental method, you are telling the system, okay, do it incrementally, do B checks, increase the back pressure if the B value is less than 0.95, increase the cell pressure for checking the checking the B values. If back pressure is not applied, the pore water pressure after the consolidation stage is 0, else it is equivalent to the back pressure. As I told you, once our sample will reach the B value of 0.95, there will be some cell pressure. Let's assume cell pressure is 300 kPa, back pressure is 250 kPa. Fine. At this point of time, once our sample will get consolidated, it means that whatever be the excess pore water pressure, that will get dissipated. So this pore water pressure will measure the back pressure that has been applied to the soil, which will be equal to 200 kPa. Fine. In case this we are consolidating it using the back pressure. In case we are using atmospheric pressure, then this back pressure, this U will be equal to 0. Now throughout the shearing process, or the consolidation, throughout the shearing process, this back pressure will be kept hold. We will not release this back pressure of 200 kPa. Correct? And during the consolidation, what we are doing is we are actually we are increasing the cell pressure. by keeping the back pressure at a constant value. Let's assume we want a confinement consolidation at 100 kPa. So we will keep the back pressure 250 as constant and increase the cell pressure by 50, because this time the difference is 50, and now by adding additional difference of 50 we will reach the consolidation pressure of 100 kPa. So I mean to say that during the whole consolidation and the shearing process, this back pressure should be kept as it is. We should not release it. So during saturation, once the saturation is complete, so U is equal to back pressure, or U is equal to 0. Fine. Now after saturation stage, confining stress is applied and drainage value is open for consolidation to happen. So once we are entering into the consolidation stage, so confining stress is applied and the drainage value is open for the consolidation to begin. So consolidation, what is consolidation? We are allowing the water to escape out from the soil, and whatever the water will escape from the soil, it will determine the volume change that the soil has undergone. Correct. So whatever the volume change that the soil will undergo at the confining stress, what we are applying, it's like a user dependent variable. So that will actually at that consolidation pressure there will be the loss of the water from the soil, and that will tell us that how much volume change the sample has undergone due to this consolidation pressure. Fine. And then we are increasing the axial load, and the pore water pressure measurements are taken. Now in the shearing stage, it depends whether we are doing the consolidated or consolidated undrained test. We have to maintain the drainage conditions, whether we want to open the back pressure drainage value, or we want to close it. So in this stage we will be determining that, we will be deciding that, and in this stage also we will be applying a deviated stress that is actually causing the failure of the soil. Now moving on to the interpretation of UU test. So we have seen the UU test. It's not consolidated, and the conditions are undrained, unconsolidated, undrained test. It's a quick test. It generally gets completed in 20 to 30 minutes. And if we talk about the stress conditions, it's a quick test completed in 20-30 minutes. It's also called a quick test. There is one more name for it. It's a quick test. If we talk about the stress conditions, so immediately after sampling, there are no horizontal or vertical stress applying. Immediately after sampling, the stress are released, vertical and horizontal stress are released. But due to this release of the stresses, due to the release and the confinement, there will be some suction that we have seen as a residual pore water pressure in the last lecture. When you are sampling the soil out, confinement is 0, but there will be a suction which will actually hold the soil sample intact. Then initial conditions, in terms of effective parameters, sigma 3 initial confinement is equivalent to UR, which is the residual pore water pressure. During saturation, we will ensure B value is greater than 0.95. In the confining stage, sigma 3 is the confining stress we are applying, which is the cell pressure application, and there is the generation of pore water pressure, and that is minus UR is the initial residual pore water pressure, and delta UC is the generation of pore water pressure due to the sigma 3. Now since B is 1, so delta U will be delta sigma 3. So use pore water pressure equation, it's done. And then in terms of effective parameters, sigma dash 3C is equivalent to QR, and sigma dash CC is again UR. Fine, because this will get cancelled with this, which will result in the same parameter. And here sigma 3 will be sigma 3 dash is equivalent to UR, because here and here sigma 3 will get cancelled. In the shearing stage, we are applying the axial load delta sigma in order to shear the specimen, and depending upon the material properties, whether it will be a dilative or a contractive, we will have a negative or positive delta U over water pressure, right? And the effective, in terms of effective parameters, it will be sigma 3 plus delta sigma plus UR minus delta sigma 3 plus minus delta U. These are the total stresses. So this plus this, right? And this plus this, or this minus this minus this. Total stress minus pore water pressure. So total stress is sigma 3 plus delta sigma minus ur plus ur minus delta sigma 3 plus minus delta. Similarly for this. So if you see this and this will cancel out, it will remain delta sigma plus ur minus delta sigma plus minus delta u. So it will come out to be delta sigma plus ur plus minus delta u, and here this will cancel out to be ur minus plus. Right. Now for like in the lab, how we are doing it, we're actually we'll take a 3 identical soil samples whose underlying shear strength we have determined, and all 3 samples have common initial state. I mean, say dry unit weight, water content, and void ratio. And once we do the sample, we will see that the response of this all the 3 tests will be same. Now, like we have 3 cell pressures, sigma 3.1, sigma 3.2, sigma 3.3, but the response is same. Why? The reason for is that we are not allowing the consolidation to happen. We are not allowing. If we are applying the whatever the confinement we will be applying from outside, due to that confinement, the sample is not getting consolidated, which may change the arrangement of the particles. It may change the packing of the particles. So it's getting only applied, but it's not getting like it doesn't have an effect on the internal structure of the soil. That's why this soil will fail at a same deviated stress, because the sigma 3 is not going to change the internal structure of the soil. So if we talk about the failure envelope in the UU test, you can see if we first talk about the for total stress, more circle for total stress. So this is the sigma 3.1, which is the in test 1, and sigma 1 is the deviated stress, the principal stress at the failure. And similarly in the second test we start with another confining stress of sigma 3 and sigma 3.2, and the failure stress is sigma 1.2, failure axial stress similarly sigma 3.3 and sigma 1.3. You will observe the diameter of this circle is constant, which means that the sample will again always fail at a constant value of deviated stress, because whatever the confinement we are applying, it's not actually going to change the internal structure of the soil, because we are not allowing the consolidation to happen. And also these are 3 more circles for the 3 tests. We are able to draw the total stress envelope. Correct? You can see there is no there is no phi component. This phi component counts when the particles will rearrange. Since we are not allowing consolidation to happen, so particle cannot slide over another slide over other particles. So the friction component will not come into play. So whatever the strength will come, it will come from the cementation or apparent cohesion of the soil. Correct? Now, if we talk about the effective stresses, so whenever, like for example, sigma 3.1 we are applying, correct, confining stress. So since soil is saturated, so same amount of U pore water pressure will be generated. So when we subtract sigma 3.1 minus this pore water pressure, it will come here, correct, and sigma 1.1 we subtract sigma 1.1 with this U3.1 to get the effective stress envelope. You will always get a single this effective stress envelope, because sigma d is constant, correct, and sigma whatever the confined we are giving, same amount of pore water pressure is getting generated. So due to these reasons, we will always get a single Mohr circle for effective stress, and that's why this UU test is a total stress analysis. There is no use of the Mohr circle, effective envelope, because we can't plot it. We don't know where the next circle lies. So there is no use of pore water pressure in the UU test. So that is the reason why I told you in the initial when I was discussing the UU test in the initial slides, that there is no use of pore water pressure, because we are not it's not useful to determine the pore water pressure, because we are getting a single effective stress envelope from which we cannot determine what is the Mohr circle envelope, failure envelope for the effective stress in case of UU test. And the strength is given by sigma 1 minus sigma 2 divided by 2, but sigma 1 minus sigma 3 rather divided by 2. Fine. And confining stress at failure is independent on the cell pressure applied. So it means that the effective stress at failure, not this is effective stress at failure. I mean the deviatoric stress is independent of the cell pressure or confining stress that we are applying, because that's not going to change the like whatever the cell pressure we are applying, it's not actually changing the internal structure of the soil. Now comparison of the UU test result for NC and OC states. NC is normally consolidated and OC is like over consolidated. For NC soil there will be generation of positive pore water pressure which will push this effective stress envelope to back side, and hence the effective stress circle shift towards left. And for the OC state there will be generation of negative pore water pressure or a suction which will actually increase the stresses. So the effective stress path or effective stress circle, it moves to the right. Now one more, it's kind of a subset of undrained, unconfined, undrained, unconsolidated undrained test, which is the unconfined compressive stress. What this test is, actually we are not applying the confining stress at all. We are simply, after the saturation, we are applying the deviatoric load. There is no, we are bringing the sample without confining it, we are applying the failure load, deviatoric stress. And in this case, the sample, the property of the sample should be, it should be able to hold this, it should be able to stand of its own. It should not need any kind of confinement. So that is why this test is purely for the fine grained soils in which the some kind of suction should exist. Loading should be quick to maintain the drain conditions, and the strength in this case is given by confined compression given by sigma 1 by 2. Whatever the load will come, divided by 2. The relevance of the undrained shear strength. The first is thing, like we know that the undrained shear strength can get triggered in the field quickly after the construction is done. Quickly after the construction there is the undrained condition. So in that case also we need to determine the undrained conditions. And change in total stress during construction does not influence the undrained strength. And at the end of construction phase, undrained conditions gets prevalent and UU becomes more relevant in these cases. As I told you, that after the consolidation phase, there is a generation of excess pore water, or the conditions prevalent gets are undrained. So this UU test becomes relevant. Now there is one more test, that's the interpretation of CU test. So let's take a break of 1 minute. After that we will start again. Okay, we will resume. Now the interpretations of CU test, which is consolidated undrained test. So consolidation at every confinement alters the initial confining stress, initial effective stress condition. That is true, because whenever we are allowing the sample to consolidate, it means that it's going to alter the arrangement, it's going to alter the water content, it's going to change the wide ratio in the sample. So it's actually changing the initial stress conditions. So that's why in these tests, consolidation under consolidated undrained test, consolidated test, this consolidation stress becomes important. Since U is measured, results can be presented in both sigma and total stress and effective stress. So in the consolidation stage we are allowing the drainage to happen, and in the shearing stage there is no drainage. It means that pore water pressure will be generated and we will be able to monitor it, and we can represent the results in terms of total stress and effective stress parameters. So let's go with the states of the triaxial test. At the saturation stage, we have to ensure always that B is greater than 0.95. In the consolidation stage, as I told you, we can do a back pressure without back pressure or with back pressure. In case there is no back pressure, the effective stresses at the end of the consolidation are given by sigma vertical is equal to sigma dash VC and sigma horizontal is equal to sigma dash HCC. Both will be equivalent to the initial total stress and vertical stress at the consolidation, since there is no back pressure. Now if we have back pressure, so vertical stress is given by sigma dash Vc plus back pressure, U back pressure, because delta back pressure will be equivalent to the UBP, as I told you, and sigma HC is equivalent to sigma dash C plus U at back pressure, and this will hold true. Sigma vertical is equal to sigma horizontal, because when we are consolidating the sample, we have to ensure that the around stress are equal, and U back pressure will be same during the consolidation, and the effective stress will be equal to sigma dash Vc and sigma dash SC. In the shearing stage, we are applying the sigma dash for shearing the sample. Depending upon the soil, we will have plus minus delta U, and correspondingly we will calculate the effective stresses. Now this holds true. Sigma cell pressure or the confining stress is equivalent to sigma vertical is equivalent to sigma horizontal. That will be equivalent to the sigma 1 dash this is equivalent to this, and sigma 3f, and this sigma 3 dash C is equivalent to sigma 3f, which is the confining stress at the failure, but which will not be equivalent to the it's not confined stress but lateral stress. It will not be the equivalent to the lateral stresses at the failure, because some pore water pressure will be generated, so there may be either increase or decrease of this lateral stress. And diabatic stress at failure is given by sigma 1 and sigma 3 at failure. Now this is the typical response of the CU test for the soils. In the last week also I have shown this has been discussed. Normally consolidated would be a strain hardening and this strain softening for the OC, while they achieve a peak. Quickly they will achieve a peak, after they will achieve a strain softening due to the dilation, and it has been, this is the plot between the diabatic stress versus the volumetric strain. And in the CU test, the volumetric response we are not able to capture because we are not allowed drainage. So due to the restriction in the volumetric strain, volumetric change, there will be generation of pore water pressure. So in terms of pore pressure, this NC will have a positive pore water pressure, which means a contraction, and in the OC it will be having a dilative response. And if we talk about the principal effective stress ratios, it is the variation is similar to the variation of stress strain plots. Now typical Mohr cycle for CU test, and if we have this is for the NC, and this is the total stress envelope given total stress for the total stress circle, Mohr circle, and this is the total stress envelope phi t. And once since in the NC there will be generation of positive pore water pressure, so these are going to decrease, so Mohr circle will shift to the left, effective Mohr circle, and this phi dash represents the slope of the fill envelope, and in this case for NC this phi dash is actually greater than phi t. However, in the total stress in case of OCs, this phi dash is greater than this phi t is greater than phi dash, correct? And due to the generation of negative pore water pressure, this effective stress path, effective stress Mohr is moving towards the right, correct? So this is written here also. Now relevance of CU test, again stability problems where consolidation already occurred and the undrained conditions are developed. For example, we have constructed this initially, then due to the construction of one, there will be generation of pore water pressure, and once this construction is over, we have started the construction of second phase. So this will again cause undrained conditions. Fine, because the consolidation already occurred after the construction of one. So whatever the construction we have done in stage one, the soil has got consolidated at that pressure. Now whatever the additional pressure will come, it will actually cause the undrained conditions. And also CU test has a relevance in rapid dry down of embankment slopes or reservoirs, where due to the rapid dry down there will be generation of effective stresses, and due to these effective stresses there will be the generation of the undrained conditions. Fine. Now you have seen the relevance of CU test. So generally this since this is generally common in clays. Why? Because they have less permeable, and in case of less permeable compared to the positionless soils, where they are freely draining soils. So there is no if the conditions will be undrained, so it will it will take less time for the dissipation of the pore water pressure. Now we have the interpretation of consolidated drainage test. So in this test, consolidation is followed by the drainage sharing. No excess pore water pressure is generated, and as a result, the test has to be done in a slow manner. So again, saturation has to ensure greater than 0.95. Consolidation can be done without back pressure, similar to the CU test, and with back pressure. Shearing stage, we have to, like, there is no pore water pressure. So as a result of which, you can see that is sigma 3 at failure. Lateral stress at failure is equal to sigma dash 3 at failure. Correct? Fine. So this was not true for the CU, and delta sigma D is equal to sigma 1 dash 1 sigma 3 dash at failure. And for the typical Mohr circle for consolidated test for NC. For NC, the Mohr circle failure envelope pass through the origin, and there, if in case there will be some deviation, if the consolidation stress range is large, because if the consolidation stress is large, there may be the kind of a cementation which can come into play and have an influence on the Mohr circle envelope, and if the initial state is different. Now this is a typical response for the OC. Mohr circle envelope does not pass through the origin. For OC, cohesion may exist and phi dash would decrease. Fine. And strength is a function of OCR for consolidation ratio and confining stress. And for determining strength parameters, samples of identical OCR is needed and subject to the different confining stresses. Now, relevance of CD, long-term stability, like when the pore water pressure is getting dissipated. So, what is the stability? Since if we talk about clays, it will not take a day or few weeks to for the pore water to get dissipated. It will take some months or years. So for long-term stability, we are actually doing the consolidated drainage test. So consolidated drainage is consolidated condition is critical for the heavily OC soils, by the OC greater than 0.4. Correct. So this was all about the a brief intro about the week 6. I know that some content I have dropped because I have to go through the problems also, and the problems have been whatever I am discussing with you, it's actually will help you to solve the problems. So now, before moving to the example problems, let's have a brief overlook on what we have discussed. So we first discussed about the triaxial test setup, how it is, what are the different components of it, and then we have went through the different stage or different type of tests that we perform. And here the paper that was time, it's a filter paper. If I just now I remember it, filter paper, I will write it here. Filter paper where we are placing the filter paper between the porous disk and sample, like here, one at here. Fine. So after this triaxial setup, we have discussed the different tests that we can perform in the triaxial, and the names are like that: consolidated and consolidated undrained. Then we went through the unconsolidated undrained test, what it is. After that, consolidated undrained. Unconsolidated undrained means there is no consolidation and the conditions prevailed during series undrained. So there is no dissipation of water throughout the test. Then consolidated undrained, it means dissipation during consolidation and no dissipation during undrained test. Undrained sharing, consolidated dissipation continuously throughout the sharing. Now the different stages. The first stage is saturation stage. The saturation stage is actually, it ensures that the soil is fully saturated and P value is greater than 0.95. And we have to take care of the point that whatever the back pressure we are applying, it should not alter the initial effective stresses of the soil. Then the use of the back pressure for saturation, and like when we are giving a back pressure, we have not to do the this B calculations immediately. We have to give a sufficient long time for this pressure to get equilibrated, and then we can do the this B check. Consolidation stage. After the saturation stage, the confining stage is applied, and I decide, like, it is a user defined value, then the soil is allowed to consolidate. So during the consolidation, water will come out, and when this volume of water comes out, it becomes constant, then we stop the consolidation stage and go for the shearing stage, where we have the preference where do the depending upon the field condition what we are what we want to study for the field soil sample, we can do the drain to undrained test, and that is like a drain sharing where the axial load is increasing and the condition will be drained or undrained. The interpretation of UV test is a quick test. Fine, these are the stress conditions in the soil, and then we see there is a there may be the different Mohr circle envelopes, but there is only a single Mohr circle envelope for Mohr circle for the effective conditions. Then the comparison of the OC and NC behavior, and the spatial test, unconfined compressed test. And in this test you have to take care of the area also, like the initial area will not be same as the final area, because you are allowing there is no confinement, so there is a chances that the soil will get bulged up, so you have to calculate the final area, and while calculating the stresses you have to divide the load with the corrected area. Fine, we will see that in the numericals. Then we have seen the interpretation of CU test, interpretation of CD test, and then some relevances of CU test. Now we will move to the numerical problems. After that, I will be here to hear your doubts. The first question, if you see, unconfined compressive test was carried out on a saturated clay sample. The maximum load the clay sustained was 127 Newton, correct, and the vertical displacement was 0.8 mm. The size of the sample was 38 mm in dia and 76 in height. Determine the undrained shear strength. Draw the Mohr circle for the stress for the test and locate SU. Now, what has been told? You have a UCS test. What is UCS? For example, this is the soil sample. You are loading it from here, and it will get filled. Let's assume it got filled here. Fine. Now, what will happen during this test is that there will be the chance it will get bulged up because there is no confinement. So the initial area A naught, let's assume initial area is A naught. Better to represent it. The initial area is A naught, and the final area AF will not be same. So we have to actually do the area calculation, and then we have to calculate the correct load, correct undrained shear strength. So how we are doing it? So what is the diameter D naught? Let's solve it. D naught is equal to 38 mm, and height of the sample is 76 mm. Generally, the ratio of the triaxial sample, if you calculate height by height, this is actually to ensure that whatever the stress you are applying, the maximum portion of the stress will pass to the sample. You have heard about that isobars and all in the stress distribution chapter. So that maximum pressure lines or contours, pressure contours should pass to the soil sample. So D naught is 38 mm, H naught is 76 mm. Can you calculate initial area? That is pi by 4 D naught square. So it is pi by 4 into 0.038 square. It will come out to be 11.3 into 10 raised power minus 4 meters square. Fine. Now the maximum load the clay sustained was 127 Newton, and the vertical displacement was 0.8 mm. The vertical displacement means let's assume we have a displacement transducer connected right here. So if it shows a 0.8 mm of reading, it means that the sample has got its height has just reduced. So what is the actual strain due to this compression? That is given by 0.8. This change in length divided by actual length is 76, which will come out to be 0.01. Now corrected area is given by A naught divided by 1 minus axial strain. A naught is 11.3 into 10 raised power minus 4 divided by 1 minus 0.01. So it will come out to be 11.4 into 10 raised power minus 4 meters square. Fine. Now we have the corrected area now, and also we have the maximum load which the soil sustained before failure. It was 127. So we can determine the maximum principal stress, that is sigma 1 at failure, which is equivalent to P divided by A. What is the load? 127, it's in Newton, I will convert it into kilonewton, divided by area is 11.4 into 10 raised power minus 4. It will come out to be 111.4 kPa. Correct? Now, what is the undrained shear strength? SU is equal to sigma 1F minus sigma 3F divided by 2. Since it's an unconfined compressive test, this will go to 0. So we are left with sigma 1 failure divided by 2, 111.4 divided by 2, which is around 56 kPa. Now we have been asked to draw the Morse law. Now, for example, for Morse we need information regarding the stresses. This is sigma x's, this is tau x's. Now, unconfined compressive strength means there is sigma 3 is 0. So we have one stress here, correct? And another will be equivalent to another, that is sigma 1F will be equivalent to 56. So we have to move, not a sigma, it's not 56. So sigma 1F is 114. Let's assume 114 is here. Sigma 1F, correct? So with these 2 points we will be able to draw the Morse circle. Fine. So once we draw the Morse circle, this point is actually our SU. This is our SU. So when we determine the value of it, this will come out to be 56. If you do it on graph paper, you will get the same value. Correct? So the main key concept in UC test is that you have to do the area correction, which is important because the initial area and final area will not be same because the sample will bulge, because there is no confinement. The confinement is 0, and then we have to determine the load P by A, which is the stress at failure, and then strength is equal to that stress divided by 2. Moving on to the another question. A NC clay is consolidated under a stress of 150 kPa, then sheared undrained in axial compression. So it's consolidated at 150, then it was sheared during undrained conditions. The principal stress difference at failure is 100 kPa and induced core water pressure at failure is 88. Compute strength parameter in terms of total and effective stress. So we have NC clay. The conditions have been given as consolidated undrained test, and the confining stress sigma 3 is given as 150 kPa. Correct? The principal stress difference, it means that sigma 1 at failure minus sigma 3 at failure is given as 100 kPa. Fine. Is true? Yeah. So what will be the sigma 1 at failure? Is 100 plus sigma 3 is 150. Let's start here. It's 250 kPa. Fine. We know sigma 1, we know sigma 3. Can we determine the sigma 1 dash at failure is 250 minus 88, it's 162 kPa. Sigma 3 dash at failure, that is 150 minus 60 minus 88, it will come out to be 62 kPa. Correct? Now we know that, let me shift it to the left so I have more space for calculation. Now we know that phi dash, in like the angle of internal flexion from the effective analysis, phi dash is equivalent to sine inverse of sigma dash 1 at failure minus sigma 3 dash at failure divided by sigma 1 dash at failure plus sigma 3 dash at failure. Correct? Can you calculate this? This sine inverse of sigma at failure is 162 minus 62 divided by 162 plus 62. So phi dash is equal to sine inverse of 100 divided by 2 to 4, into 26.5 degree. And similarly the phi is equal to sine inverse of sigma 1 at failure minus sigma 3 at failure divided by sigma 1 at failure plus sigma 3 at failure. So when you put the values of sigma 1f and sigma 3f, you will get phi is equal to 14.5 degrees. So here also you can see that the effective is greater than the total stress. Now we have another question similar to the question 1. Unconfined compression test is conducted on a soft clay. The specimen is removed from the undisturbed tube sample and is now 35 in dia and 80 mm in height. The load on the force transducer at the failure is 14.3 Newton. The axial deformation is L1 mm. Calculate the unconfined compressive strength. So similarly, as we do in the question number first, we will first determine the axial strain. Axial strain is delta L by L. Change in length is 0.11 mm. L1 divided by 80, which is 0.1375. Fine. Now A corrected is equivalent to A naught divided by 1 minus E. A corrected is pi by 4 into 38 square divided by 1 minus 0.1375. It will come out to be 1115 mm square. Now sigma 1 at failure is 14.3, which is lower divided by area 1115. And if we convert into the kPa, then we have to write 10 raised to minus 3 into 10 raised to minus 6. This will be equivalent to 12.82 kPa. Fine. So SU will be equivalent to sigma 1 at failure divided by 2, which is equivalent to 6.4 kPa. Same question. Now moving on to question number 4. So we have SU test was conducted on a saturated clay soil by isotropically consolidating the soil. SU test. So it has been isotropically consolidated using a cell pressure of 150 kPa. Then increasing load on the plunger while keeping cell pressure constant. Failure was observed when the stress exerted by the plunger was 160 and pore water pressure is 540. Find SU and find SCS. Since in this case the sample has been concentrated under the atmospheric pressure, I mentioned that cell pressure has not been introduced. So here the cell pressure, consolidation pressure will be equal to the cell pressure. So you have been told sigma 3 is equivalent to 150 kPa, correct? And this sigma 3 has been kept constant till the failure, and the failure happened when the load was increased from the sigma 3 to 160. So sigma deviatoric at failure is equal to sigma 1 at failure minus sigma 3 at. So sigma d is given as 160. So 160 is equal to sigma 1 failure minus 150. So implies sigma 1 at failure will be equal to 310 kPa. So what is the effective sigma 1f? So it is 310 minus 54. It will be 256 minus 310 minus 4, 256 kPa. So we have the sigma 3f. What is the sigma 3 dash f? 150 minus 54, that's 96 kPa. So SU under initiation will be sigma 1 at failure minus sigma 3 at failure divided by 160 divided by 80 kPa. And phi dash CS again will be equal to sine inverse of sigma 1 dash at failure minus sigma 3 dash at failure divided by sigma 1 minus sigma 3. fine. Sigma 1 dash at failure minus sigma 3 dash at failure divided by sigma 1 dash plus sigma 1 sigma 3 dash. This 256 minus 96 divided by 256 plus 96, and we have a sin inverse here. So this 5 dash here should be equal to 26.7. So this is the way generally we used to solve the problem and find the friction values for the whether it's a critical state or the strength parameter. Right. Now the last question is a UU test, unconsolidated undrained test, was conducted on saturated clay. The cell pressure was 200. So sigma 3 at failure is 200 kPa, and failure occurred under a Dweck stress of sigma d at failure is 220 kPa. Determine undrained shear strength. Now we know that SU is equivalent to sigma 1 at failure minus sigma 3 at failure divided by 2. The sigma 1 can be written as sigma 3 at failure plus sigma d at failure minus sigma 3 at failure divided by this and this way. Sigma d is 220 divided by 2 is equivalent to 110 kPa. So the undrained shear strength will be equivalent to 110 kPa. So that's what, like, in this question, in these problems we have seen that how we can approach a different problem for understanding, for determining the undrained shear strength or strength parameter, whether it's phi or the unconfined compressive strength, and also the the strength parameter in terms of total analysis or effective stress in terms of effective stress, and the strength parameter in terms of total stress. Fine. And also more separate representation for the unconfined compressive strength test. So that was all for today. So I will stop the recording here, but I will be there in the meeting up to 5. So if you have any doubt, you can raise hands and tell me, or we have a forum where you can ask the doubts. Our mentors are there to help you at each moment. So see you. Just go through these lectures, go through the content that I have delivered today, and I hope with this content you will be able to solve the assignment, and you will get good marks in this assignment, or you will get a good content out of this lecture. Thank you. See you next week.